This is a walkthrough of Problem 2 on Exam 1 of Module 3, which can be found on page 69 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 2 is, the equipotential lines in a field region are parallel. Here they are, these dashed vertical lines. They're 2 centimeters apart. Conventionally, the voltage falls in the direction of the field, so the direction of the field in this figure is to the right. What is the magnitude of the electric field at point A? Part B, a particle with a mass of 20 micrograms is shot in from the right. It has a speed of 100 meters per second at the minus 100 equipotential line. The field stops it at the 50 plus 50 volt equipotential line and sends it back the other direction. What is the charge on the particle? We know the particle's got to be positive because the force is to the right, the field is to the right, particle must be positive. We have to figure out the magnitude, but let's focus on part A. We already have a good diagram. For part A, we know the field drops 50 volts every 2 centimeters. The field must be 25 volts per centimeter to the right. That's part A. Part B. The particle stops after traveling through a voltage difference of 150 volts, which means it lost 150 joules for every coulomb of charge it has. We can calculate its kinetic energy. 1/2 mv squared. I converted 20 micrograms to kilograms, so I can get joules, and I get 10 to the minus 4th joules. If we know the energy change was 10 to the minus 4th joules, and we know it lost 150 joules per coulomb, we can calculate what the charge is. There's the energy. The change in kinetic energy is Q delta V. Delta V is 150 joules per coulomb, 150 volts. And there's the charge, 6.67 times 10 to the minus 7th coulombs. That's the answer to part B, but let's do it again. Let's do it a different way. What's the acceleration of the particle? We know it goes from here to here, which is 6 centimeters. Minus 100 to plus 50. 2 centimeters, it drops 50, that's 6 centimeters. Started at 100 meters per second, stops in 6 centimeters. We can calculate the acceleration. V final squared equals V initial squared plus 2ax. We can substitute in the knowns. Ends up at rest. Starts at 100 meters per second. Stops in a distance of 6 centimeters. We can solve for A, and we get minus 83,300 meters per second squared. From the acceleration, we can get the force because we know the mass. F equals ma. The force is 1.667 times 10 to the minus 3 newtons. If we know the force and we know the field, we can get the charge. F is QE. We calculated the field in part A. There's the force. There's the field, 25 volts per centimeter, which is 2,500 volts per meter, which is 2,500 newtons per coulomb. And we get exactly the same answer, not surprisingly. That's problem 2.